Hey everyone, my name is Kyle Yu. I was a Red Hat intern over this past summer working on the Octo team Emerging Technologies, and I am a data science student at Boston University, and today I'll be talking about GPU programming with Triton. So just to give some context on the big picture, as we know, is very important in AI and deep learning. So if we think about large language models that are being developed by Google, Meta, OpenAI, um, even just a small percent of increase in efficiency or optimization in throughput or latency can save loads of money. So even a 1% can save millions of dollars. So that's kind of like a little background on kind of moving forward into what GPU kernels are. And so a GPU kernel is a function designed to execute in parallel on the GPU, essentially allowing to maximize the performance of a certain operation or routine, and to maximize, squeeze all the performance we can out of the GPU. So most notably, we have CUDA, which is a C++ extension to run on the CPU and GPU. Except the problem with CUDA kernels is that it's very hard to, you have to have a very deep expertise, many years of experience, knowing GPU architecture, and as well as is very time intensive to develop, taking over many weeks and even months to develop a very efficient kernel. And this is just an example of a very simple CUDA kernel that one may write. As you can see, it's very, you have to really understand the deep GPU architecture to really write these kernels. So what does that take us to? That takes us to Triton. Triton is a Python-like domain-specific language, and it's specific for GPU programming. The nice thing about Triton compared to CUDA is that it abstracts many of the low-level details that of not having to understand as much of the GPU architecture. It does that all under the hood for you. And as well as it's open source, developed by OpenAI, started out of research in Harvard, and is now being developed. OpenAI took the main developer, and now they have a big team developing Triton over there. As well, compared to CUDA, it supports both NVIDIA and AMD GPUs, compared to CUDA, which is only supported on NVIDIA. So just to give some, I guess, an example and walk you guys through, how many of you guys heard of Triton before or worked with Triton kernels? Okay, a couple of you. So just kind of to give like a more intro example, this is a vector addition kernel. And at the high level, it's a bunch of workers running on the GPU, computing many small vector additions in order to compute a full output of a longer vector. So at the top, we have a Triton decorator in order to tell Triton that this is a Triton GPU kernel rather than just a regular Python function. And we have 5 different inputs. So the pointers are basically pointing to the GPU device arrays for our X and Y pointers, which are the vectors that we're going to be adding, as well as the output pointer, where we're going to put our output in the GPU device. And elements is the number of elements we have in our arrays that we're going to be computing. And the block size is essentially getting how many elements in each worker group that we're going to compute against. So first, each worker is defined a program ID in order to keep track of which elements our workers are working on. And so that's defined by the PID using the TL.program ID. And in order to figure out where's the worker going to start in the arrays, we define the block start. So for example, if we're on the worker 1 and our block size is 32, our worker will start on the index 32 of our arrays. And in the offsets is essentially defining the specific index elements that we're going to be working on. So for example, if we're on block start 32 of index 32, we want to get from 32 to 64, which is our block size of 32. And mass is essentially making sure we don't go out of bounds when computing these vector additions. And so as you can see, we have loading right here, the X and Y batches using tl.load, as well as the X pointers for finding the device or the array on the GPU, as well as using the offsets to make sure we're grabbing the specific smaller vectors that we want to compute in this specific worker. And as well as the mass, so we don't go out of bounds when computing these kernels or computing this output. And it's very simple. We just have a very simple X plus Y, which computes the simple vector addition within this worker and within the specific array. And finally is the tl.store, specifically pointing it back to the output pointer on our GPU device, using the offsets as well, so we make sure that the output is in the right order. And yeah, that's kind of your first kernel for you. So yeah, just to give a little bit of background about the specific work I did with Triton Kernels at Red Hat. I was working, some of my teammates are here actually. Craig was helping me with Triton BLAS. So I was working on 2 different kernels. My first is what Craig called it a doozy kernel, because there was a lot of difficulties with global reduction and figuring out that jazz. So that was a lot of fun. So I had to develop a multi-kernel structure in order to deal with the global reduction and kind of getting that all into one output, as well as a GemV kernel or matrix vector multiplication, where I found 70% gigabits per second increase in throughput over the PyTorch benchmark on AMD GPU. As you can see in the top right, we have my benchmark on the GemV performance. And finally, which was inspiration from my L2 norm kernel, which was a lot of struggle, I developed a Triton Misadventures repository as an educational resource for others to learn about Triton and basically learn from the mistakes that I made, because it was definitely a struggle, and I hope people don't have to go through that. And finally, I guess to end it off, I was playing around with AI-generated kernels. There's tools like Kernel LLM and Mako, actually Mako does a lot of kind of the generation as well as the benchmarking and validation portion of it. So that was also very nice to kind of see how new tools are developing in the space in AI-generated kernels. But that's all I have for today, and I hope you kind of learned a little bit about Triton. And if any of you have any questions, yeah, go ahead.
Store operations.
So yeah, the loading essentially is grabbing it from the GPU device into this worker group, and then the TL.store is sending it back to the GPU device for our output array.
So these going from GPU to CPU?
Not GPU to CPU. It's basically putting it onto the GPU for the workers to work on. So
okay.
Not GPU to CPU, but
within the GPU.
Yeah, within the GPU. Yes.
Okay.
Yes.
Okay. And what is TL itself?
TL is the Triton. It's Triton.
Okay. Okay.
Triton, yeah.
All right. Yeah. Very cool. Wait, how was the GPU mode hackathon?
Oh, it was a lot of fun. Yeah, it was New York, and it was a lot of PyTorch optimizations and batching as well. So
okay, it's very cool.
Yeah.
I was also a Red Hat intern.
Right.
I'm slightly envious of the project you were able to do. It's very cool.
Thank you. I appreciate it. I was very lucky to have a great team supporting me. So,
All right. Thank you.